Hi everyone and welcome to this lecture. So in our previous lectures we promised that in this lecture we are going to talk about adjoint. There should be an I over here. We are going to talk about adjoint, self-adjoint and Hermitan operators, and we are going to discuss why they are very important for us, especially for physicists. And let's get started. So let's say I have an operator. Let's say there is some operator L in our infinite dimensions. So the adjoint of this calligraphic L will be given by L dagger. Now you might ask, what if L dagger equals to L? Can't I call that a Hermitian operator? Well, no. There will be something else as well, because we will clear this in a minute, because we are dealing with infinite dimensions, so we also have to verify that whatever we are doing is justified with our definitions for infinite dimensions as well. So we won't draw any analogy with the finite dimensional case. So this L dagger will be our adjoint. And how do we define a self-adjoint operator? Because in the last video I told you guys that the Hermitian operator will come off as a special case of this adjoint operator. So let's now talk about self-adjoint operators. So how are they defined? They're defined via the following. This relation, let's say you have two functions and these are my test functions, and let's say they are defined over some interval a and b, where a is the lowest limit on the integration and b is the highest limit. So this f star x and this L operator acting on the g of x integrated with respect to x will give me a b, and I'll have this L dagger that will act on g of x, and this thing will be conjugated as well over here, and finally I'll have gx dx plus some boundary terms. So what are these things? I'll explain to you in a bit. This is the integral representation, and if you recall that we defined the inner product via integrals in infinite dimension, you can actually write them in a more compact notation. So if you write them in the bracket notation, this will just be, not straight L, the calligraphic L, G like this, and this will be just G L F, where this will now act on G rather than acting on F, and this is understood, and this whole thing complex conjugated plus the boundary terms. Any operator L that satisfies this relation 1 is called a self-adjoint operator, and when the boundary conditions are 0, this boundary term goes to 0, they are known as Hermitian operators in infinite dimensional case. And this is the definition you can start with and have this expression, or you can start with this definition and find this bracket notation convention. So let me just now give you guys some example. The first example we are going to take is that if I define my operator L as the second derivative, that is d squared dt squared, and our functions as the test functions, that is, these are our test functions that will help us to determine whether this L is a self-adjoint operator or not. So these are my test functions, and again they are, let's say, they are just defined over some interval a and b. So instead of, sorry, I should have written t, not x. So This is the interval of interest. So to do that, we are going to seek refuge to this definition over here, or this one over here. They're the same thing. This is just the integral representation. This is the bracket notation thing. It helps us to save some of our pages, let's say. Also our time. Also this is easier to understand. So let's start it. So if you just directly refer to this thing, first you see that L will act on G, right? So from now on, I won't write f of t and g of t explicitly. It will be well understood from the problem itself. So let's write as a, b. We'll write f star, then the second derivative of g, like this, and we'll have our dt. And then what we do, a physicist's favorite friend is integration by parts. So do integration by parts. You will have some f star, then dg dt evaluated at these boundary points, alright, and minus again ba. You will have the derivative operator, because if you integrate it by part once, then you will have to leave whatever this dg dt is, and you will have to find the derivative of this f star. So finally you'll have df star dt, dg dt, and dt over here. And here you have to integrate it by parts again. So let me just put this sign for saying that this symbol is there, or this term is over there. These are the boundary terms. And there will be some more boundary terms after we do this integration by parts over here. If you do it, integration by parts again, you will see that what we're having is that we'll have this g of t, and we'll have df star dt evaluated at b a, and this minus, and there will be another minus coming in, because every time you do an integration by parts, you pick up a minus sign. And finally you'll have ba, and g will be over here, and this guy over here, that is df star dt, will get differentiated again, and finally you'll have this second derivative, right? Okay, so let's write this thing in its full glory. So this is df of our f star dg dt evaluated at my boundary points. I'll have g df star dt ba plus this little integral over here. Oops, there should be a dt. Yeah, dt squared, because this is the second derivative. And now if you compare it, let me just write this left hand side down again so that you can easily compare this thing. If you compare it with this one over here, you can see that this is a similar structure, because L was this d squared dt, right? So let's write it again. That is ba f star L, that is the second derivative with respect to 2 defined over here, and then this is acting on g over here, right? And we have our integration measure, and these guys are called the boundary terms, because they are evaluated at my boundary points, right? So these are our boundary terms. So let me just write them down as boundary terms. And finally you can have this plus this integral b a. And now if you look at it, this is the adjoint, because you see that there is no complex term over here, right? So the adjoint of this thing will be just this thing itself, right? d squared dt. So, and this is acting on what? Our f star, right? So we can write it as L star, and sorry, L dagger with f star, with that is acting on f star, or you can write the whole thing like this that we wrote before, that is L dagger is acting on f, and you are taking the complex conjugate of the whole thing, right? And there is just g, and there is dt. This is entirely similar to the definition we provided above, that is this definition. Okay, yeah, this definition. Or again, you can just write these things down in a more compact notation. F L G equals to this G L F, this whole thing star. Obviously L will now act on G, and then there is this boundary terms. So this tells us that L, that was defined as d squared dt squared, that is the second derivative operator with respect to t, is indeed a self-adjoint. Operator. Now you might ask, okay, this is a self-adjoint operator, but these boundary terms, they're there, right? And is there any way I can make them 0? Because I told you that whenever you take these boundary terms to be 0, the self-adjoint operator will become a Hermitian operator. And because why? An Hermitian operator has real eigenvalues, and to get rid of to get these eigenvalues real, these boundary terms have to be taken to be 0. And in physics we can do that. So if you define your functions, let's say this is your a, this is your b, and this is your f. It looks like a wave, so this is, let's say, f of x, and you have your g of x like this. So you can see that f of a equals to g of a equals to 0. Similarly, f of b equals to g of b equals to 0. And not only that, our derivatives over here are also can be taken to be 0, but not always. So instead of taking the derivatives to be 0, it's better to stick with the functions, that is the functions you are defining, and you say that the endpoints are not varying. So when can this happen, right? Let's say this a goes to minus infinity and b goes to plus infinity. So whatever is happening at the infinity, we don't care. We take them to be static. By static, I mean they're 0. So these are the things that you will see when you deal with quantum mechanics, especially in wave functions and all that. So this is how you can similarly prove that the first derivative operator is not a self-adjoint operator, and as a result it cannot be a Hermitian operator as well. So before I finish off these discussions on linear algebra, I want to introduce the eigenvalue problem. Problem in infinite dimension. And I want to do that via Schrodinger equation. So the Schrodinger equation is the heart of quantum mechanics, that whatever you are going to do there, and it will turn out to be that you have to solve some Schrodinger equation, then you'll get some wave function or the energy eigenstates and all that. But let's say you have an operator. Okay, let me just get rid of this hat, and obviously this color is not that suitable. So let's say you have an energy operator that is known as the Hamiltonian operator, and it is given by p. This p is an operator by 2m, and let's say we are dealing with a harmonic oscillator, so this will how the Hamiltonian will look like, and this p and x, they are operators. And let's say there are some states defined by this n, and these are called energy eigenstates, because this is a eigenstate that corresponds to this operator. So that's why we're calling it an energy eigenstate. So the eigenvalue problem will be that we have our operator h, we have our vector n, that is an energy eigenstate. It should spit out the energy for that level. This n will refer to some level, that is some energy, and it will leave the vector as it is. So now let's say we want to, this is the abstract thing. The question is, there might be some way to do it, right? And the idea is to represent P in the coordinate basis as following. Since we are dealing with one dimension, I'll just take this to be dd of x. And as I already mentioned, this dd of x is an anti-Hermitian operator, and energy is something observable, right? So the trick is, since you are getting a minus sign and you don't want a minus sign, the trick is to put an I and put a minus sign over there, so that when you conjugate it, that is when you evaluate it like this, like we did before, you get a you don't pick up any more extra minus sign, and this whole thing becomes a Hermitian operator. And this x will be just they will correspond to this code. Let's say you have a coordinate basis, and they will just correspond to this eigenvalue problem. So now you might ask that how do we represent this abstract thing in some basis, right? That is, we have to take a basis, that is, we have to take some projection, and the idea is to go to the coordinate basis. So let me just write it down. The idea is to go to or take the coordinate basis. Take the coordinate basis. Take the coordinate basis. That is, you are projecting this whole thing into the coordinate space. That is the space with x, y, z, the familiar coordinate that you're familiar with. So how can we do that? We can do this via h, n, like this, and here you will have this en. This is a number. It will ignore this bracket whole thing because you can take it out, and this will be x and n. And this thing over here, that is the projection of the energy eigenstate into the coordinate space, will something that will be written as psi of x, something also that is called a wave function. So let's accept this, and what will happen over here, that because of this x is acting from the left, we will get this representation. This p will be represented by this ddx of thing, and this x will be represented by this. And if you do all of that, so this will finally turn out to be something like this, h cut square by twice m. And you can see that the Hamiltonian had p squared, so there will be a I square and ddx times ddx, right? So this will correspond to a second derivative. So there will be d square psi. I'm not writing the x explicitly, something like this, and here you'll have 1/2 of m omega squared, that is the frequency of the oscillator, and small x square. Note that this is not the number, this is just coming from this eigenvalue equation, something you learn in more details when you do quantum mechanics. And there will always be a psi over here, and finally you will have E psi. So the eigenvalue problem finally reduced down to solving a differential equation. Whether we can solve it or not, that's a case that we're going to talk later after midterm, that is when we deal with differential equations. But this is the idea, that this eigenvalue thing you learned in finite dimensions is also appearing here in infinite dimensions, and this time there is a differential equation. And after this and this will, that is this example here, will conclude the discussions we are having on linear algebra, and after midterm we are going to see how we can actually solve this kind of differential equations. In fact, talking about differential equation will be very similar to talking about linear algebra as well, and we will try to see how we can connect these two seemingly different topics, and we can see that how they're really connected and how they help us in solving physical problems. So this will be it for today, and thank you.